Syzygy episode 102, Breaking the Universe. And welcome back to the Syzygy podcast, episode 102. My name is Chris Stewart, and I'm in the office of Dr. Emily Brunsden here at the University of York. Emily, hi.
Hello.
We did it 2 weeks in a row.
I know. It's
we
amazing.
should have one of those little party popper things to and confetti goes everywhere. Those of you who haven't been tuning in for a while, this is a big deal for us because Emily's got a small disease incubator known as a child at home,
Yes.
and it's been a pretty rough couple of months.
Whew,
Yeah, but we are here, and this is good. So today we got some stuff to talk about, Emily. We're going to be talking about really, really old galaxies.
Yes.
Galaxies so old, they're not just breaking the internet, they're breaking the entire universe. They're universe breakers,
Yes.
which sounds like that can't be good.
No, not really.
Okay.
No one would recommend breaking the universe.
No, best not to if you can avoid it. So we'll come to that in a minute. But before we do, Emily, got a question for you. What time is it on the moon?
Well, it depends on who you ask that question as to what your answer is going to be.
Yeah.
But it is a very important question that we need to know the answer to.
It's one of those really deceptively simple questions like, oh, what time? Well, surely it's, I don't know. What time is it on the moon? Does that even make sense?
Yeah. Well, historically, when we've done lunar missions, we've just adopted the time of whoever's running the mission. So if it's a NASA mission, they just use, Houston time, whatever, as the current time. But if you're a Chinese space probe, you might use Chinese time, for example. Now, that would kind of work if there were just a few individual missions going up, coming back, and it didn't really make any difference to anybody else. The problem is that the moon is going to get quite popular over the next decade.
It's going to get busy.
Yes.
Yeah. Lots of people going to the moon, lots of things going to the moon.
Exactly.
Yeah.
And some of these people and things are going to want to talk to one another. And to do that, they need to be on the same time. Because otherwise, if you say, let's meet up for a coffee at whatever.
At the Sea of Tranquility Starbucks at such and such a time. Whose time? What time? Is that Chinese time? Is that American time? Is that Japanese time? Is it Australian time? Is it UK time? Does that even make sense? And I mean, that's what we've done for past missions, right? We've just, if America sent up something or someone to the moon, they just went, well, we're just going to use, Houston time or whatever it is. And they have, relay stations in space to just send signals back and forth. And they go, well, it's this time because that's the time it is back on Earth. Because frankly, that's where the rest of us are. Mm-hmm. And all the people who were looking after this mission, they're down in America. And so we're using that part of American time. But that's not going to work when we've got more and more people and more things driving around on the moon and more missions and so on. So we've got to come up with lunar time.
Yeah. Well, it's interesting because we do have Mars time, right? So Mars,
yeah.
Then you have Sol and a particular number, right? So the Martian days are measured in Martian time, and all the missions on Mars will measure things in Martian time.
How long's a Martian day relative to an Earth day?
It's a bit longer, I think.
A bit longer, but
so,
it's in
and
the
year
order
is
of...
obviously a bit longer.
Yeah.
So everything gets measured relative to Martian time, and that's fine because then everyone's talking the same language, if you like.
Sure, and then that kind of makes sense because Mars is a really long way away, and you can imagine being on a different planet. You kind of need a different day, but the moon's close enough that I kind of just. The first time I came across the question, I kind of thought, well, it's the same as Earth time, isn't it? Because it's just the moon. But no.
Yeah, it isn't, I guess. So you could say, well, let's just take lunar days. The problem is, particularly if you're dealing with people, is that a day on the moon lasts for 29 and a half Earth days.
Yeah. And you kind of forget that because down here on Earth, the moon just passes by and we see it every day, and you don't tend to think about the fact that no, from the moon's point of view, it's pointing at the sun for half of a month, right? It's a 28 roughly day cycle, which means it's 28 days for it to go around the Earth. And because is it tidally locked? Is that what it's called?
It is, yes.
So the same part of the moon, same face of the moon is facing us all the time. That means it takes 28 days for the moon to rotate, and that's a day. So 28 Earth days is one lunar day.
Even just a little bit more. As I say, it's just over 29. But
which is a really long time to stay awake.
Yeah, exactly. And so, saying, can you, on Saturday, can you please go and check this particular instrument? That could be several months away for an astronaut.
Yeah. So that's never going to work. No. So with all of this stuff coming up, there's lots of missions going to the moon. There's people going back to the moon sometime soon. I noticed this week, I think NASA was announcing that they're going to announce who it is that's going to be on that first human mission back to the moon again, first one since the 1970s, which is all very exciting. But before then, kind of got to work out how are we going to do time? And part of the way they're going to be doing that is by, well, we were talking a little bit about this last week. They're going to be putting up the equivalent of not global positioning satellites, but I guess lunar positioning satellites. Network of satellites around the moon so that you can tell where you are really, really accurately, the same way we can on Earth, which is very cool.
And what time it is, of course.
And what time it is, which is really important.
And those satellites are going to have to get general relativity on board because the moon does not have as much mass as the Earth. So you're in a smaller sort of gravitational well, which means time passes very slightly differently on the moon.
Which, as we mentioned last week, might sound like a completely theoretical thing. But actually, when you're talking about wanting to find your position on the ground or on the moon's surface to within a small distance, you need those tiny little corrections from special and general relativity to get it right. Otherwise, you'll find yourself in a completely different crater, and no one wants that.
And your houseboat will be on top of the hill.
Yeah, or your lunar buggy will be down a pit somewhere, and that's not good.
No.
Yeah. So that's kind of fun. Anyway, I saw that in the news this week and I thought we should probably talk about it because it's an interesting question if you've never thought about it before. But anyway, enough of that. Let's get on to the topic du jour, which is really old galaxies. Stupidly old, unfeasibly old.
Are they old or are they young? That's another question.
Well, okay. You tell me then. What are we talking about here today?
So we're coming back to our favourite space telescope of the day. Well, second favourite. Tess is always going to have.
Tess will always have our hearts on this podcast. Everyone knows that. But, Tess aside for a moment, our favourite one is...
James Webb.
James Webb. Just wonderful space telescope.
So we've got a new result which came out at the end of last month where James Webb has detected 6 massive galaxies. Now, we'll come back to what massive means. But big galaxies, which are dated to actually be so far away, so old, that they were only just born not very long after the Big Bang itself.
Right. Doesn't seem right.
Well, the problem is that they're too big to be in existence in just the few short 100 million years, few short hundreds of millions of years that has occurred from the Big Bang to the point where now we're observing them.
So this is why this new bit of research is being broadcast out there on the airwaves as these are universe-breaking galaxies.
Yeah, there's not enough mass in the universe at that time in the right places to form these galaxies according to our standard model of cosmology.
That sounds like a problem.
Yeah.
Yeah.
Could be.
Yeah. Okay. So first of all, why don't we break with tradition? We have a bit of a tradition on this podcast of forgetting to mention who it is that we're talking about. Who's done this research?
So this is a group led by Labbe et al. So a really nice group of people who were looking at some of the very early releases from James Webb from middle of last year. And it's a nice paper. It's a Nature paper that's come out. Interestingly, it's still in what they call accelerated print.
Which means what?
Well, it means that they haven't checked it for spelling and grammar.
Have they checked the science?
Yes.
Oh, well, that's good.
Yeah.
It doesn't matter whether it reads properly as long as the science is correct.
Yeah, so it's a little bit of an odd one in that sense. So
that is a bit odd. I mean, don't get me wrong. This sounds like important, groundbreaking stuff, but couldn't we just take a little bit longer to check the spelling and the grammar? No one's going to die if we take a little bit more time to work this one out.
Well, that's the point of accelerated print. It's get it out there. We'll come back to doing the nitty gritty, fine tooth comb over it. Obviously, when people write something, they don't, turn off spell check and just write any old nonsense. Yeah. So it's a well written paper. Let's be honest. But editors from journals always fuss. They like to fuss with the exact wording of particular phrases, and they have a style which the journal has to sort of conform to.
Okay, so that's all to come.
Yeah.
But for the time being, hey, you might be interested in this result. So let's just get that out there.
Exactly.
All right, so tell us a bit more about the result then?
Okay, so there's 6 galaxies which are found to be dated around about 600 million years after the Big Bang.
Now, just a little reminder, the Big Bang was how long ago? We think the universe is 13, but what's the latest number?
13.7,
13
yeah, 7-ish,
billion
yeah.
years. So we're
Yeah.
talking more than 13 billion years ago
Yes.
was when these things were formed.
Yeah, so basically the universe was only about 3% of its current age. So a few 100 million years sounds like a lot, but on the scales of the universe, it's absolutely nothing, right? This is Big Bang, boom, there's now huge galaxies.
And I mean, let's be clear, there was a lot going on in those first 100 million years of the universe. A lot's happened by that point. You could imagine that there is definitely stuff and structure and things forming all over the place. But it sounds like the problem of this one is, but when you add it up, when you do the calculations, when you run it through the models, there's not enough time for this to happen.
Exactly, yeah. So in terms of what actually happened since the Big Bang to this point, let's say, in the universe. So we've had our Big Bang, we've had this kind of very, very rapid growth period of the universe where it just went bananas in terms of expansion. It's a period we call inflation. So that's all happened. We had the cosmic microwave background, which we've talked about previously. That's been emitted. That was 380,000 years after the Big Bang. So that's when photons were sort of free to whiz around the universe as they pleased. Now remember that the Big Bang was really hot and bright and, so basically hot and dense was the universe. And it takes time for the universe to expand and cool. So from that point of the cosmic microwave background being released to the point of what we say that the first stars managed to form is a period we call the Dark Ages, because the universe was too hot for like hydrogen to come together, collapse, and sort of squish up to that. It started nuclear fusion. It was too hot to do any of that.
I mean, it's a bit bizarre to call it the Dark Ages because it was too hot. That implies that the whole thing is glowing bright. But what you mean by that, I'm guessing, is it was dark in the sense that there were no nuclear reactions happening in the way that we see light from stars now.
There was no
dark
stars.
In that way.
There were no stars, so there was no starlight, so it was dark.
Sure.
That's kind of
Let's go with that.
The argument. Yeah. So, and we think that should have taken at least a few 100 million years to turn on the first stars.
Just to get stars?
Yeah.
Okay.
Because you need to cool down enough for then gravity to take over to pull everything, a big clump of gas and dust together to make a star. Now, we have these are not the oldest galaxies that we've ever seen. The record holders for that particular honour were actually found also by James Webb not so long ago, in December last year. And they are a few galaxies that were found to be round about 350 million years after the Big Bang.
I kind of feel like we have talked about this.
We did mention this, in our return episode.
Yes.
These really, 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 really new, like brand new spanking galaxies in the universe. Of course, to us, they look really old, and because it's been a long time since the photons left those galaxies and travelled to us. So it's kind of a mixture of, are they old, are they young? But in the timescales of the universe, they're really young. But those galaxies, which are found at these huge, huge distances, and we're going to talk a lot about redshifts. So I'll say these numbers and you will come back to them after we've discussed what redshift means. But these are redshifts of kind of 12, 13. These are hugely distant galaxies.
It's one of those few measurements in astronomy where the number is actually really small, but it means a lot.
It means a big distance.
Yeah,
exactly. But these are small galaxies. These are things that are maybe, 1,000th the size of the Milky Way galaxy.
Wow. Okay,
so
that is small.
They're just little tiny things. So they're fine in terms of cosmological models. We can kind of understand how little they're not really much more than clusters of stars, really, can form, that sort of in that time scale in the universe. That's not too bad. The problem is that with these galaxies, which are around about that 600 million year mark, these ones are just huge. So there are some of these 6 galaxies, I think 1 or 2 of them, which are the size of the Milky Way.
Right.
And that's too big.
It's too big.
Too soon.
We can't make that happen.
No. So how do you get something that's as big, that's as mature as the Milky Way in just the couple of 100 million years is the big question.
Yeah. Now, either, it sounds like to me, either we're getting the age of these things wrong, or we're getting the size of these things wrong, or we're wrong about how long it takes to do a galaxy of that size.
Yeah, everything could be wrong.
So everything could be wrong.
Yeah.
So I guess that's the point here. Is
Yeah.
we've got these great models, we've got these great ideas about how the early universe was going, how galaxies form, how the first stars and the first galaxies came together. And a lot of it works really, really well. And then every once in a while, JWST or equivalents say, okay, we found this one, doesn't work. And we have to figure that one out. And that's presumably why this one's making a few headlines. Astronomers, cosmologists getting a bit hot over the fact that it doesn't work. Our models don't work.
Exactly. So if you take that these measurements are exactly correct, that the masses of these galaxies are exactly correct, then you've got a problem with our standard model, which we call lambda CDM, or it's a model of the whole universe that we have that includes dark energy and what we call cold dark matter, or kind of the best description that we have of dark matter.
All the bits that we think we know about built in there doesn't work.
Yeah. And it should work because it's a very good model. Let's not, I mean, just because it's got like these mysterious things like dark energy and dark matter in them, which, okay, we don't know a lot about those things, but we do understand how they impact the universe reasonably well. So the model itself is robust, and it has been robustly tested in hundreds of different ways and found to be a good fit to what we see in the universe.
It's a fascinating thing that you can have models which are based on stuff that you don't know what it is, but it doesn't matter. We don't need to know what it is. We just need to know what it does. And we know what it does, dark energy, dark matter, know what it does pretty well.
Yeah.
So we can build that into the models. Doesn't matter if we don't know what the stuff is itself.
So having something that upsets the model would be a big deal.
Yeah, but also kind of exciting.
Yes, absolutely. Well,
okay,
it would
all
mean
right.
something
So how do we dig down into this problem then?
Well, so let's have a look at what these galaxies are and how they're being measured, because that was a big if, I guess, that I put out there, that if these measurements are exactly correct. So we've got these galaxies, 6 of them, and they go from, as I say, 600 million years. And they do range a little bit in size. There's something like tens of billions of solar masses. So you could imagine tens of billions of stars like the sun, up to hundreds of billions of solar masses, or hundreds of billions of stars like the sun.
Which is where we are in the Milky Way.
Yeah, we're about 300 billion.
Okay.
So, a Milky Way-ish size, which is, we're not a small galaxy.
It's
let's
a
be
decent
honest.
size for a galaxy.
Yeah, we were all right on the galaxy scale.
We can be proud of this.
Yeah, exactly.
Collectively.
Yeah. So how do we actually do this? How do we make these measurements of something that's so distant and so faint? Well,
I'm glad you asked, because I have no idea. I was assuming that was a rhetorical question.
Well, you take one James Webb, of course.
Yeah, that's a good place to start.
That's an important factor. So we measure something called the redshift. So the redshift is a proxy for the age of an object, because as we look into the deep part of the universe, we're looking back in time. Photons take non-zero amount of time to get to us, right? They can only travel at the speed of light.
Yeah.
So photons from the sun take 8 minutes to reach us here on Earth. Photons from distant galaxies take billions of years to reach us, right?
And I mean, this is true everywhere. Like, I'm looking at you across a table and you're about 2 meters away. And so you are 2 light meters further back in time from me. But that's irrelevant, utterly irrelevant. Like, there's such a tiny little error in the calculation. It doesn't matter. But if you start looking at astronomical distances, then distance equals back in time. Okay. Now, how does that then translate into redshift? What's that?
So what's been happening is, since those photons left that very, very early galaxy, say 13 point whatever billion years ago, they've been whizzing through the universe. But the universe has been doing stuff underneath that photon. The universe has been expanding. So that has changed the wavelength of the photon, the frequency of the photon. And because the universe is expanding, it's stretched the photon. So a photon had a wavelength which might have been kind of a blue color, for example, when it left a galaxy. Over time, it gets shifted and shifted, makes it redder and redder and redder and redder till it goes all the way through the colors of the rainbow, all the way out to the infrared part of the spectrum.
Which is quite bizarre when you think about it. I mean, as the space time itself is stretching out, the universe expands. That's what that means. It breaks your brain a little bit to think, well, I mean, surely stuff's just passing through that, though. But no, what it actually does to those light waves is it stretches those out, and a longer wavelength is down the spectrum in the redder direction, which is what we mean by red shift. We shift in the red direction, or beyond red into the infrared. But,
exactly.
But yeah, that's what we mean by that. Whereas blue shift goes the other way.
Yes. Yes.
You get blue shift sometimes when something's moving towards you.
Yeah.
Then the light can be blue shifted. But in this case, stuff coming from the universe, through this expanding universe, is always red shifted.
Almost always.
Because of the expansion of the universe.
Exactly.
And so, as you said before, what was the phrase? That redshift is a proxy for distance
age.
And therefore age.
Yes.
Yeah. Okay.
Yeah. So the more redshifted you are, the longer that photon has been flying in the universe. Therefore, the further away that galaxy is, therefore the older it is, or from our point of view in time, or the younger it is in terms of the time frame of the universe.
Right. Yes.
That's a lot.
Okay. I'm glad we've clarified that one.
Yeah.
Good.
Yeah. So when you talk about numbers of redshift, as you say, they're actually fairly sensible numbers for astronomy, which is useful. But they represent enormous distances.
So you were saying before redshifts of sort of 12 or 13, which seems like that's quite a small number. That's what you said, wasn't it?
Yeah.
But that translates to what?
Well, those numbers will translate to something like 30 to 40 billion light years away.
30 to 40 billion light years away. Okay, I've immediately got a question.
I know what your question is.
Okay, those of you paying attention at home, we said before that the universe was 13.8-ish billion years old. Emily has just said that the light coming from these galaxies is redshifted by an amount that would say that they are 30 plus billion light years away. And it doesn't take a degree in astrophysics to work out that 30 billion is considerably larger than 13.8 billion. So, Emily, where am I going wrong in this very fast back of the envelope calculation? It doesn't work.
It's a very common, tricky thing to get your mind around.
Okay, let's try.
So it's tricky, but it actually makes a lot of sense as well. The thing is that when that photon that you're measuring now left that galaxy, but that photon has been traveling 13 point whatever billion years in its journey to reach us here on Earth, right? That is true.
Yes.
It only travel at the speed of light. That's only how much time there's been in the universe. Those are your limits. You can't break them.
So let's visualize that amount of time.
Yes.
Good. Okay, 13.8 billion years. But that's not 13.8 billion light years away.
No, but what happened is since that photon left that galaxy, the universe has expanded.
Oh, so the thing that they left
has
moved away
from us.
Right.
So when we receive that photon, to measure its distance to what the distance is to the galaxy right now, we have to push rewind on the expansion of the universe, bring that galaxy all the way back to where it used to be in terms of where the photon left it.
Right. It's a little bit like when you hear a plane go overhead. I mean, it's not exactly like this, but it's a little bit like this. A bit like when you hear a plane go overhead and you can hear it and it's up there in the sky. But by the time the sound gets to you, the plane has moved. And so if you look to where the sound seems to be coming from, you won't see the plane.
No.
Because the plane's moved in that amount of time. You have to look over here now. So, there it is up there, but the sound's coming from over there. This is kind of similar, that the light left the galaxy and then the galaxy, well, the universe, moved the galaxy further away.
Exactly.
So 13.8 billion years in time translates to more like 30 to 40 billion years in actual distance. Okay.
So our observable universe, so the universe that we have access to, because the photons have been traveling for 13 point whatever billion years, is about 46 billion light years across.
Right. Okay.
Or in
Considerably
each
bigger
direction.
than the 13.8. Yeah.
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 Okay. That makes sense.
So that's exactly where
yeah,
things are right now.
that makes sense.
Yeah.
Good. Right. So that's where we are. We've talked redshift. We talked how that translates into distance. And we've established the fact that a redshift of, say, 12, 13 is a really long way away.
Really, really long. Yeah.
Good. Okay.
So if we go back to these galaxies, what we want to do then is to find, it's always been one of the main scientific missions of James Webb is to look into the very earliest part of the universe, the first stars, the first galaxies.
Yeah. That was the thing when we talked about James Webb last year, getting very excited about its launch and then starting to look at its, very first data download. James Webb was going to be able to do pretty much everything for everyone in some way. But this really was one of its big selling points was we're going to look at the very earliest things.
Yeah, it's what it's built to do.
Yeah.
And it's built to do that because it's in the infrared. So those galaxies which would have had light in the optical, for example, coming out when it was emitted, all that light's been shifted down to the red part of the spectrum, down into the infrared part of the spectrum.
So if you want to go and look for those things, your Hubbles aren't going to work nearly as well because Hubble is very much in the visible.
Mostly,
right?
yeah.
Mostly. You need something down in the infrared, and that's
Exactly.
what JWST is.
Yeah.
Cool.
So the way we do this is we're looking for very red things, right? But there's lots of very red things in the universe. The question is, how do you tell something that's just red because it's red?
Red, yeah.
Or it's red because it's been redshifted.
Right. Okay. Yes, sure.
That
would be a problem. You could confuse those two.
It's
things.
a non-trivial problem,
Sure.
actually. You want to know.
Sure.
So,
because if the only thing that you're looking at is the color of the light, like that's all you've got. You've just got the light coming from the thing. Then you need to be able to make that distinction.
Exactly.
Yeah.
So you've got a little red blob that you've taken a picture of, and you want to find out how far away this blob is. You want to measure how red it is, but you want to know, is it red? Why is it red?
Is it just red?
Yeah.
And really close by?
Exactly.
Yeah.
So there's a technique called the Lyman break technique. And this is a really interesting one. I quite enjoyed reading up a bit more into depth about this. So there's two ways that you can measure redshift. And this is let's say the easier way to do it. So the way that we would normally in kind of astrophysics say you need to measure redshift very, very accurately is you need to take a spectrum. So that means you take the light from the star or the galaxy, you break it up into all its constituent wavelengths, and you look at the lines which will be shifted from where they would be normally found, say, in a laboratory.
Right. And the lines being the sort of the chemical, the atomic, the elemental fingerprints, right? That hydrogen, when it gets excited, emits light of very specific wavelengths. And so does helium, and so do all the other things.
Yep.
They all emit their own special fingerprint at very specific wavelengths. And so you can look for that and go, okay, well, that's hydrogen, except it's not where we'd expect hydrogen to be. It's over here. It's been redshifted. And so you can compare hydrogen in the laboratory to that hydrogen that we see in the spectrum of that star and go, this is how much it's moved down the frequency or down the wavelength
Exactly.
axis.
Yep. Turns out, though, that process of spectroscopy is it's tricky, right? And it requires quite a lot of light, because imagine you're taking those photons, you're breaking them all up into the parts of the spectrum. You need a lot of light to do that very accurately. And by definition, we're looking at things that are really, really faint.
Yeah.
So it's not easy to do this. But there is a sort of slightly easier way that you can do it, which is through not taking that full spectrum and looking at every little gory detail, but taking kind of chunks of it. And to take a chunk of a spectrum, what you do is you use a filter. So just like you might get different tinted coloured glasses, they're just basically filters. So if you get blue glasses that make the world look blue, then all it's doing is just letting in all the blue light.
Yeah.
Right?
Cutting out the other colours and letting the blue stuff through.
Yeah.
Yeah.
And you can have a blue filter, you can have a green filter, you can have a red filter, you can have an infrared filter. And indeed, James Webb has loads of these filters. And the nice thing is that you're not throwing away as many photons as you would be if you were doing a spectrum. So it's easier to get, say, 10 filters and take a picture of maybe a whole bit of the sky at once even, and take that in 10 different coloured filters and compare the different coloured filters. It's easier to do that than it is to get a really good high quality spectrum of a single galaxy.
Okay. I'll have to think about that one a little bit more. That's not immediately intuitive to me. I kind of feel like if you're putting a filter on, aren't you're cutting out light already? So why does that make it better doing a load of those rather than just saying, just let all the light in?
So it depends on it's your resolution. So what you would do with a really good high resolution spectrum is you would say, we're going to make the boxes of box size, say of 1 nanometer. And we're going to have 1 nanometer, and we're going to count how many photons are in that 1 nanometer.
Right. So you're zooming in. If you imagine a graph of the spectrum, or literally looking at a rainbow, for example, right? Looking at a rainbow, you are looking at the spectrum kind of as a graph. You're looking at light as a graph, where how much light is there at the yellow, how much light is there at the green, and when you're talking about a box here, you're basically saying how much are we going to zoom in on that spectrum and say, well, when we say yellow, do we mean this particular bright
wavelength,
yellow as opposed to the slightly greeny yellow or the slightly bluey yellow?
Yeah.
Right.
So to do a spectrum, you need to have lots of little tiny boxes, and you need to have lots of photons so that you can measure what is in each box. Right?
Okay.
So when you do filters, however, your box sizes are huge. You might have 100 nanometers in a box. So you're collecting all the photons that are in that 100 nanometers and putting them together. So you've just got a lot more photons to play with in your box.
I'm prepared to believe you. I still need to think about that one a bit more, but clearly I'm wrong and you're right. So let's go with that.
It's like taking a very very coarse spectrum, which is easier than doing a very, very fine, high resolution spectrum.
Okay.
So you can do these filters, and you can switch through the filters, and you can look at the same galaxy in lots of different filters, or indeed, as James Webb has done, you can look at a huge patch of sky in lots of different filters. You're not focused on just one galaxy. What's really cool about this data is that it all comes from a patch of sky that was chosen, which includes the Hubble Deep Field, the ultra deep field, actually, which is kind of cool because we've spoken about the ultra deep field before. It's this tiny little patch which is of sky
that Hubble stared at for ludicrous amounts of time and made this image which is full of dots, and you think, wow, that's a lot of stars, and then you realize it's not stars. All of those dots are galaxies.
Yeah.
There's thousands of them in this tiny little box
something like a pinhead at arm's length.
It's ridiculous.
And we didn't think there was anything there.
Yeah.
It was just a bit of black sky.
Turns out full of galaxies.
Yeah. So the ultra deep field is a very humbling image because it's the emptiness of space is actually just full of galaxies.
So James Webb is looking at a larger bit of sky, but it also includes that piece.
Yeah, and that's
just
where this
for
comes
overlap,
from, which is kind of nice.
Yeah.
So that's just an aside. But anyway, so you can look at a patch of sky, and you can look at it in all these different filters, and you look for galaxies that do particular things to say these are the old ones. These are the ones that come from the very early universe. And this is where the Lyman break technique comes in, because there's a very special thing that hydrogen does. Hydrogen is useful, most abundant thing in the universe, right? We've got loads of hydrogen to play with. So that's great. And what happens is that in the intergalactic medium, or the space between galaxies, there's a wavelength which below that wavelength, hydrogen gets absorbed and you just don't see it anymore. So all the hydrogen spectrum is just gone. We just can't see it.
And why is that? What's getting
so it's just all the stuff in the intergalactic media. It absorbs it. It's just gone. It just gets removed from all the
stuff.
Space.
And so if you add up everything that is happening all along the way in between something and us, below a certain wavelength, it's just all gone. It's all absorbed. Okay.
Which is, so the Lyman part is typically below about 91 nanometers, or if you're a micron person, it's 0.09 microns. That's our laboratory rest wavelength of hydrogen. If it's below that, it's sorry, if it's above that, was above it in hang on, we got to do this around the other way. So if it's wavelength shorter than that, then it's blocked out by the intergalactic medium. If it's wavelengths longer than that, then it comes through to us. So you've got this very hard edge, and that's what's called a break. Because it's like 0, and then you get to the longer wavelengths, and it's fine.
So it doesn't just sort of fade out. It's a fairly hard cutoff.
Exactly.
Right.
Yep. Now, you can look for that cutoff and see where that cutoff is, because we know where that cutoff should be in the laboratory. If you can measure where that cutoff is in a distant galaxy, then you can measure the distance to that galaxy.
Right. So in this case, you're not looking at specific, say, hydrogen lines, lines of sort of, the energy levels of hydrogen. You're looking at something which is a bit more generic or broader than that, which is this cutoff.
And the reason is because galaxies get so faint that you can't even see the individual hydrogen lines by this point. They're just,
but you can see the difference between we have light and we don't have light.
Exactly.
Stuff's getting through, stuff's not getting through, which is that break.
Yeah.
Yeah, I can see how that's useful.
If you take a high resolution spectrum of this galaxy, then you'll see nothing jump.
Right.
And
that's the break.
Brilliant. Yeah.
And you can see that.
Now, we don't have the high resolution spectrum of these galaxies yet, but we can do a clever thing with our filters, and we can say, okay, we can look at the blue one. Does the galaxy exist in our picture with the blue filter on? No. Does it exist when we have the green filter on? No. Does it exist when we have the red filter on? No. Infrared. Oh, look, there it is. It jumps into existence. So therefore, we can say that the break must be somewhere in between the red and the infrared filter.
Sure, because the light is getting through. You can't see it at the other ones, but you can see it in this one. So the break's somewhere between those two filters.
Exactly.
Cool. Okay.
Yeah. And so that's the technique of measuring the redshift, because you know that therefore the break is at approximately this wavelength. Measure the redshift, measure the distance. You're all sorted.
Very clever.
It is
I like
very
that.
clever.
That's smart.
It is smart.
Yeah.
And actually, this particular study used not only a single break, it used a double break technique. So it used two lines or two little jumps in hydrogen. So it used this Lyman one, and it also used a Balmer one, which if you're familiar with your series in hydrogen.
Yes, those of you who've studied hydrogen in physics or chemistry at school or at university, the Lyman series, the Balmer series, really important energy levels series in hydrogen.
Yeah, so we've got these two breaks. And so they're using two just to kind of really be sure that we get this measurement
correct. It's a good check, right?
Yeah.
If you get the same answer for both, you're on the right track.
Yeah. So they took these big images with hundreds and thousands of galaxies in them and applied this, said, okay, we want galaxies that aren't there in the blue, in these bluer filters, but they pop into existence in these more red filters, and we want to measure those two breaks, make sure they're in the right sort of places, and then we'll say that they're old galaxies.
Great. Okay.
Yeah.
So that all turned out fine, and everything fits with the models, and we can all go home.
Yeah.
No.
As an aside, though, I do have something exciting for you.
Go on then.
So part of this analysis was done with a piece of code, which we have mentioned on this podcast before, that has a very cool acronym.
Oh, we love our astronomical acronyms on this show. They're some of the best ones. If you can crowbar half of the alphabet in, even better. So go on then.
This is still one of my favorite ones. It's one that, if you recall, came from Scotland.
Oh. Is it so? It's a Scottish themed acronym?
Of course it is.
Is it like haggis or something?
It's even better than that.
Oh, really?
It's bagpipes.
Oh, okay. I do remember that coming up, but I could not possibly tell you what it stands for. What is it?
I can tell you
before you even start. I know that they've worked hard on this one get it to bagpipes.
It's a little bit contorted. I'll give you this one. I won't make you guess. It's Bayesian analysis of galaxies for physical inference and parameter estimation.
Do you know what? I've heard worse. The ones that really bug me are the ones where you have to drag in letters that aren't actually in the name or that are like several letters down the word. And that one works.
Yeah, the ES is questionable at the end, but hey.
Yeah.
Whatever.
That's really good. Bagpipes. Okay, cool.
So we have bagpipes.
It's an acronym for an analysis. Let's move on from that one. Let's not spend too much time on it. But that's nice. Cool. Bagpipes.
Yeah, so they did the analysis. Now, what's interesting is that the media, of course, they'll draw out any old, tiny little crack in a story and run with it.
Well, I mean, if astrophysics, if cosmology is going to get into the news, it's got to have some kind of foothold. And that foothold's going to be, oh my God, we don't understand anything. Or the biggest, the oldest, the fastest, the scariest.
We're all going to die? That's also a good one.
That's always a good one. But in this case, they're jumping on these galaxies can't possibly exist kind of story.
Yeah, or they're going to break cosmology, which is even worse.
Yeah.
So actually and I always find, we've done this several times actually, where we've had these very controversial things, and yet you go and read the paper, turns out the paper itself lists all the reasons why this may not be quite right.
Who'd have thought that things get blown up in the media? But
scientists
anyway,
actually do have integrity.
Yeah, we have thought about this. We're not idiots.
Yeah. So, or does it really break cosmology?
All right. So
That
spill
is
the
question.
beans.
Right. So in the paper itself, I mean, there's, as you actually very nicely summarized before, there's three possibilities here. Either our models are not quite correct, or our measurement of the redshift is not quite correct, or the measurement of the mass, the size of these galaxies, is not quite correct.
Okay. So any of those could be wrong, and that would explain these results. Because coming back to this, it's been a while. We've been talking for a while. Coming back to just remind us of what the problem is here. We've got these galaxies which are really old and quite big. And so by the models, they shouldn't be there. There wasn't enough time between the Big Bang itself and when these galaxies seem to be, which is what did you say, around the 600 million year mark after the Big Bang? And that's not enough time for them to have formed at that size, according to the models.
Yeah. If you want to be really dramatic, there's not enough baryons in the universe at that point.
Right. And that's a problem. If you haven't got enough baryons in your life, that's going to cause all sorts of things. So something's got to give.
Yes.
And it could be one of those three things.
Yeah.
So talk us through it.
Well, okay. So the first one, the models might not be quite right. Now, this is not saying we've broken cosmology. We're going to throw out lambda CDM. We need to start from scratch. Actually, everything we know is wrong.
Wipe the blackboard clean.
That would be baby in bathwater scenario, right? We're not going to do that.
Yeah, that almost never happens.
No. However, models might need a bit of a tweak, you know? I mean, we set up our cosmology based on observations. We're very good at observing the universe around us nearby. We have great observations of how the universe works in the, close to us. Moving far away from us is hard.
You said before, one of the things built into these models, this great model of cosmology of the universe, what is it, lambda?
CDM,
it's not chat GDP, it's lambda CDM. One of the things built into that is dark energy. We've only known about that for a couple of decades.
Yeah.
Give us a break. You know, we got to get this stuff right.
Yeah, so lambda CDM works wonderfully in the universe today. It works really well in the early universe, but, there are some assumptions that we make from observations of the universe we have today which may not be applicable to the early universe. Maybe there was a different type of cooling that happened. Maybe the dark ages were a little bit shorter than we thought that they could have been. Maybe the dark matter clumped a little bit quicker. There's some possibilities of what I would call very minor tweaks to the model which would help change, this whole schism of the two.
Yeah. I could imagine a relatively minor tweak on large components of the universe, like dark matter, for example, which would shift stuff like when did these galaxies form, or how big are they, or, such things, by enough to make it say, oh, no, that makes sense now.
Yeah.
Okay. Yeah. No, we got that.
Exactly. So, and one would be completely unsurprised if something from James Webb ended up tweaking our models of cosmology, because that's what it was built to do.
That's the whole point. That's why we put it up there. So these news reports of, oh my God, we've broken cosmology. Well, kind of, that's what we're trying to do.
Yes.
We're testing this stuff.
Exactly. So there's that. But there's also, measurements. We need to maybe refine our measurements a little bit here. Okay, so we've got this technique of the Lyman break. As we said, that's using filters, these large buckets that are taking, large bins that are taking lots of photons. A much more precise way of doing those redshifts would be to take a proper high-resolution spectrum.
Right, which, as you said before, that's really hard to do because these things are really, really dim.
Yeah, but turns out James Webb can do it.
Yeah.
So guess what's in the telescope proposals for James Webb? Can we please go back to these galaxies and observe them in high-resolution spectroscopy?
We're going to come back to that with James Webb. Good.
So those proposals are in, and it's up to whoever's deciding, what James Webb's going to look at next as to when or if those galaxies get observed with those instruments.
So that's, that's in the the pipeline. It's in the could we please have a look at this phase. But like, what kind of time scale? If you're working on this is your research, how long do you have to wait before you get to do that check?
Well, that's a really good question. So what happens is with James Webb is you put together a proposal, and there'll be a deadline. I'm not sure if James Webb is quarterly or semesterly. I suspect it might be quarterly, but there's a deadline, and everyone says, I want to observe blah, and everyone puts in a proposal, and there is a committee that then goes through all those proposals and says, yeah, that's a really strong case, we're going to do that one not quite as important, so maybe let's not do that one, because there's only a limited amount of time and resources.
There's only so much time that a telescope can do anything.
Yeah, so the proposals that are accepted will then be put in the queue, and it depends on then what the most efficient way is to run the telescope as to when your particular set of observations will come up. So a year, maybe, I would say, somewhere like that.
I was expecting you to say, like, it could be years, like years and years. And it's like, oh, that'd suck. But a year, you know.
Maybe something like that. I would imagine this would be quite important to follow up on. But hey, what's my opinion? Not much. So
you're not on the committee.
I'm not on the committee. Okay. So, but I would imagine it will come up at some point.
Okay.
So let's see. We'll wait. So we got to get a really good redshift, and that will help us because, you know, maybe there was another reason why these galaxies appeared a little bit redder than they should have. Is there a bit more dust in our line of sight, which means things are a bit redder? You know, have we got the ages of the stellar populations or the actual composition of the stellar populations correct?
Right.
By that I mean, are there actually just lots of really red stars in that galaxy? Are there lots of massive blue stars? You know, actually telling how not every star is the sun in a galaxy. How many big stars are there? How many small stars?
These really early ones were quite different.
Exactly.
But if you can get that really high resolution spectrum, I mean, hydrogen is hydrogen.
Mm-hmm.
And as far as we know, always has been. So if you can see the actual lines, the actual fingerprints, then that will tell you much more accurately or much more conclusively, no, we really are talking this far away, this far back in time.
Yeah.
Yeah.
And then improving on the models of how much mass there is. Like I say, you've got to figure out, what is the distribution of mass? Are there lots of big, heavy stars? Are there lots of little stars? And how do you know that? What are your models based on? Many of them are based on galaxies that are, again, close to us. So they're in the late part of the universe, whereas the early universe was probably really different.
So how do you work that out?
Well,
how do you understand the things that you're looking at in order to understand the things that you're looking at? That doesn't make any sense. It's a circular argument.
Well, you can use some input. So we know the universe was a different composition than it is now, right?
Mm-hmm.
There was much more hydrogen and helium proportionally than things that aren't hydrogen and helium, which are loads of stuff we have today, all the other parts of the periodic table, the rest of it, right?
Yeah, all the other stuff.
Which has come from the life cycles of stars. So before you had the life cycles of stars, there was pretty much only hydrogen and helium. So you run models of what stars that are only built out of hydrogen and helium do. And there are lots of different groups who are looking at what might these early stars have looked like, what might the galaxies that they're in have looked like. So there's some interesting stuff like literally going on right now.
I mean, again, people are thinking of these things.
Oh, yeah.
This is not sort of, we didn't think of that. No, we are thinking of that. We're doing the work right now.
Exactly.
We've been doing it for a while. But again, a relatively minor tweak into one of those could translate into, that makes sense now. Yeah.
Exactly. And even the galaxies themselves may have been quite different. So in the universe around us, we don't see very many what we call active galactic nuclei, or big supermassive black holes in the centers of galaxies that are actively feeding off matter from the galaxy, sending out huge amounts of jets, huge energy,
we
light.
talked about these on a few episodes of the podcast. Amazing things, but not near us.
No.
Which is probably a good thing.
Oh, yes, definitely. Yeah. So they're not super common in the what we call the universe today. They were around, but not many of them.
Yeah.
But they were much more common in the early universe. So we've got to put some of that information into the models when we decide how big this galaxy is, right? So there's some big open questions about how to calibrate those results in terms of the mass. Obviously, we want to get better measurements of the redshift. And I think even the cosmologists are quite happy to sit down and say, actually, here's some observations. We need to adjust some little tweaks here to get our cosmology on board with those.
So we're not short of possible explanations for this discrepancy. This is not a bunch of cosmologists just beating their heads against the wall, gnashing and wailing and going, "It's all broken. We don't know what we're doing." No,
absolutely not.
No, we've got this covered. And not only that, this is exciting because it means great. We get to figure out stuff.
And even anticipated, right?
Yeah.
I mean, everyone knew James Webb was going up. And we had a long time to get used to the idea that James Webb was going up.
Yeah. These kind of surprises have been waiting in the wings for a very long time.
So if you're a cosmological theoretician, then you're going to sit there and wait, what are the possibilities? What happens if I tweak the universe by this? If I adjust this by this? You know, people sit down and think about that for many, many years before James Webb even flew. So it's not that shocking.
It's just kind of made me think. We've made this comparison a few times, I think, over various episodes. Like I used to be a particle physicist, right? The other end of the size scale. And when the Large Hadron Collider came online, and one of its big things was, can we find the Higgs boson, right? This special particle associated with a special field in particle physics, which is responsible. It's the part that allows us to understand where mass comes from. Like, it's really important, but no one had ever seen it before. And there were all sorts of theories about what this Higgs part of particle physics might look like. And a really simple one was, well, maybe it just looks like this. And the Large Hadron Collider, they flicked it on, did a huge amount of evidence, like data collecting and analysis, and then went, yeah, it's that. Oh, like, that's great, really good, and Nobel Prizes all round and all of that. But it's been like a decade since, and they've been going, is there anything else? Like, give us something else to play with? Like, the early result was, yep, this is what we expected. Oh, you sure? Like, can you just give me? And what they're really hoping is to get more information. This stuff with JWST is kind of the opposite. It doesn't work with your models. It's different from what we expected, and that means we get to improve what we do, which is even better in a way.
It's wonderful. And even the paper itself. So the paper does postulate, actually, it's probably the truth, quote unquote, or the answer is somewhere in between all these observations. Probably, some further observations will push these galaxies to be maybe a little bit later in the universe. Possibly, probably, or they'll be a little bit less massive than we thought they were. And our cosmology will just need a tiny little tweak to some of the values here and there. But it's not really, I would say, life-changing to physicists, let alone to anyone else.
Yeah. So as you say, this is expected and we've got it covered.
Yeah.
We know that we're pretty sure that we're going to work this one out with a bit more information, a bit more data, a bit more working out. And that's the fun part.
Exactly. I mean, this is great that we can see into this part of the early universe. I came across, when people were talking about this, lots of people quote this particular Carl Sagan quote when things like this pop up. And the quote is, "Extraordinary claims require extraordinary evidence."
Yes, which is a good quote.
It is an excellent quote. I would add to that and say, well, that's great. We've got an extraordinary telescope.
Extraordinary claims require extraordinary evidence with an extraordinary telescope.
Yeah.
I get that on a T-shirt.
Yeah.
I like that. Right, well, finding our way out of this particular podcast, I think you've just come up with a really good design for a new T-shirt for Syzygy there, Emily.
Well, there
I might have to put some effort into that on the weekend. We'll see where we get to. So, what have we learnt today? We've learnt, everyone out there in listener land, that when you see a headline in the mass media about, oh my goodness, this new discovery has just broken cosmology, you know that is, science's version of Bettridge's law, right? Bettridge's law is, if you see a question mark in a headline, then the answer is invariably no. The astronomical equivalent is, did that just break science as we know it? The answer is no. No, it didn't. The scientists have got this one covered. We just need more information. We need to work stuff out, and that's a good thing.
Yeah. Can I offer another piece of advice?
Please do.
So when reading nature papers or nature articles on the website,
which we all do all the time.
Well, yeah. There's a turns out I didn't really notice this until now, but there's a comment section at the bottom.
Oh. Don't read the comment
Don't
section?
read the comment section.
Yeah, but I mean, that's just a general internet rule, right?
It's the dark half of the internet.
Never scroll down. Even on Nature? Really?
Oh, and especially on cosmology papers or papers that have anything to do with cosmology.
But what do you find?
A lot of very, very bad theories that people harbour about the universe.
A lot of armchair theoreticians going, well, actually...
A lot of people who are very uncomfortable with the fact that the universe is expanding and therefore have to create a personal kind of theory of a steady state universe that meets that philosophical need.
Never
it's very
scroll
odd,
down.
isn't it?
Never scroll down on the internet.
Don't do it.
And listen, speaking of the internet... We are on the internet. We were just having a little chat about this before we started recording, and we often talk at this part of the show about, like, are we on the interwebs? Are we not on the interwebs? What social media are we doing? Look, we've made a decision.
We have.
In 2023, listeners, we're going to give Twitter a bit of a wide berth from now on, for all the reasons that you can possibly imagine. And if that's disappointing to you, sorry, but that's what we're going to be doing. On the other hand, we are still out there in other ways. Emily, how can people find us on the interwebs?
Yeah, well, I think we discussed that if you're above a certain age, you might be interested in looking at things like Facebook.
Facebook, yep. So for our older listeners, our
That's
Facebook
me included,
style,
by the way.
Well, me as well. Yeah. We are on the Facebook.
Yeah.
And as Facebook does, you just go and search for us. Put in the little search box.
SYZYGY.
Podcast. You'll find us.
Yeah, we're there.
But for the younger listeners...
I think the more hip people are on Instagram, so we'll give that a go.
I mean... The really hip people are probably on like your TikTok and your Snaptagram or whatever the hell it is, and we're not doing that.
No,
right?
no,
but Instagram.
We
is
have our limits.
Yeah, that's where we'll be. And of course, we have a website.
Oh, that's the best.
Yeah,
I love that the most.
syzygy.fm, syzygy.fm, and it's where you can find all of the information about all of the 102 episodes that we've done of this podcast. All the images that go with it, all the details, everything. Plus, our great wall of thanks to all our fabulous supporters and patrons who have supported us over the years to keep the electrons flowing through the website. And if you want to become a supporter, that's the other place that you can go, is patreon.com/syzygypod, where you can throw a couple of bucks our way and help us to do what we do.
Yeah, you got me the shiny new mic.
That's exactly right, Emily's. If you're thinking, gee, Emily's sounding good, it's because we've got her a new microphone, which is very exciting.
It's not an afterthought of the laryngitis or anything.
Anyway, listen, we do need to bring this one to a close. So just before we do, the last thing I'm going to say is, if you really want to help out the podcast, the way you do it is you share it around. You go and tell everyone you know that there's this thing called the Syzygy podcast, and it's awesome, and they talk about the universe at large, and share that around, because the more people who listen, the more we can feel like we're actually doing this job well. So share it around. But otherwise, Emily, this is 2 weeks in a row we've been doing this. Should we go for 3?
I think we should. Trifecta.
All right. Fingers crossed. Keep your fingers crossed, everyone, and we'll catch up with you in a week. See you later, everybody.
See you later.
Bye.